Ever get this feeling like the universe is holding out on us? Like it's got these secret ingredients, hidden rules, not quite ready to share.
Oh, absolutely. It's like there's this whole other side to the story we haven't uncovered yet.
Right. Well, today's deep dive, we're all about prying those secrets loose. We're talking hidden sector physics. Basically, a world of particles and forces that interact with ours so weakly they've flown under the radar. Until maybe, just maybe, now.
And what a discovery that would be. We're not just talking about adding a few more characters to the particle zoo here. This could completely rewrite our understanding of, well, everything. Fundamental forces, dark matter, you name it. It's like suddenly realizing there's this whole unseen ecosystem thriving right under our noses.
Okay, I am hooked already. But let's back up for a sec, full detective mode on this one. Our main clue is this scientific paper called LHC Probes the Hidden Sector. So where do we even begin? What makes physicists think this hidden world even exists in the first place?
It's not just wishful thinking. It arises naturally from some of our most well-established theories. Think of it like we're trying to put together a puzzle, right? And we keep finding these gaps, these places where a piece should fit but doesn't quite add up.
So the hidden sector might be holding those missing puzzle pieces.
Exactly. And not just that, it's not just about finding what we don't know, but also explaining what seems a little off about what we do know.
I like that. So how does our paper say these hidden sectors might be linked to ours?
Well, it lays out three main ways. Imagine our universe as this bustling city, right? And the hidden sector is like, I don't know, an underground network running beneath it.
Ooh, I like that visual. Go on.
So there could be these secret tunnels, hidden passages, places where these two worlds intersect, influence each other subtly.
Secret connections waiting to be traced.
Uh-huh.
Okay, I'm already picturing a map with all these dotted lines. So how do we start mapping this hidden world? Give me the rundown on our prime suspects.
Well, our paper zeroes in on three main players: hidden photons, axion-like particles, and mini-charged particles. Each one, like a phantom, leaving these incredibly faint fingerprints on our world that physicists are trying to detect.
Let's start with those hidden photons. The paper mentions something called kinetic mixing. Is that how these ghostly particles make contact?
It's one way and a fascinating one. See, hidden photons are like the shy cousins of regular photons, the particles that make up light. They want to interact with our world, but they just don't quite speak the same language.
I see. Communication breakdown.
Exactly. So kinetic mixing, it's like a temporary translation service, lets these hidden photons borrow a bit of a regular photon's identity. That way they can interact with our matter and forces just ever so slightly.
So they're putting on a disguise, blending in just enough to pass unnoticed, except for the faintest of traces.
You got it. And this is where the LHC, the Large Hadron Collider, comes into play. It's not just a giant particle collider, you see. It's also a phenomenal detective tool.
How so? Like a giant magnifying glass, helping us spot these tiny interactions.
More like a giant net, really. By smashing protons together at these insane energies, the LHC creates a shower of particles. And physicists, they're hoping that within that shower, they might find evidence of these hidden photons, momentarily dropping their disguise, revealing their true nature.
And what have we found? Have we finally caught a glimpse of these elusive particles?
Well, here's where it gets really interesting. While we haven't found conclusive proof of hidden photons yet, the data from the LHC, specifically from its ATLS and CMS experiments, it's allowed scientists to set some limits.
Limits? Like on how big they could be or where they could be hiding.
Exactly. Well, more like limits on how strongly these hidden photons can mix with our own photons, depending on their mass. It's like saying, we haven't spotted Bigfoot yet, but based on our research, we're pretty sure he's not living in this part of the woods.
Okay, I like that analogy.
Yeah.
So we're narrowing down the possibilities.
Precisely. And the really exciting part is that these limits, they're constantly being refined, pushing further into uncharted territory. If you look at Figure 1 in the paper, it really drives this point home. The LHC is already exceeding the sensitivity of previous experiments, especially when it comes to heavier hidden photons.
Okay, I'm looking at Figure 1 now. It's pretty clear. The LHC is giving us our clearest look yet into this hidden world.
And we're just getting started. Remember, the paper also points out that hidden photons might interact with our world through something called higher dimensional operators.
Okay, hold on. That sounds like we're venturing even further into the realm of science fiction.
Yeah.
Are we about to open a portal to another dimension?
Not quite a portal, but you're on the right track. Think of it more like a bridge. A temporary connection between our familiar 3D world and another dimension that we can't directly perceive.
Okay, so not a physical portal,
Hmm.
but a way for these dimensions to sort of touch.
Yeah, exactly. And these higher dimensional operators, they describe how particles from these two realities could briefly interact across that bridge, even if they can't fully cross over.
Okay, I'm trying to wrap my head around this. So we're not talking about hidden photons putting on a disguise to mingle with our particles, but rather reaching across from their side to ours. And the LHC can detect that.
It can. It all comes down to energy. Remember those particle showers the LHC creates? Well, if these higher dimensional operators exist, some of that energy could be channeled into creating hidden photons, or even other hidden sector particles we haven't even talked about yet.
And because these interactions will be governed by, the laws of physics, they should leave behind telltale signs, like a cosmic calling card.
Precisely. And just like with kinetic mixing, the LHC's data is helping us narrow down the possibilities. Figure 3 in the paper, it focuses specifically on these higher dimensional operators. It shows the limits the LHC has placed on how strongly hidden photons can interact with the different types of particles in our world.
Hold on a second. The paper mentioned something about different flavors of particles. Does that mean there are, like, chocolate and vanilla hidden photons out there?
I wish it were that simple. Flavor in particle physics, it's just a way of distinguishing between different types of particles that share some fundamental characteristics. Like, for example, electrons and muons, they're both leptons, a type of fundamental particle. But they have different masses, and they interact with other particles in subtly different ways, hence different flavors.
So it's more like we're trying to figure out if these hidden photons have a preference, like they prefer to interact with certain flavors of particles over others. Do they have a favorite?
That's the million-dollar question. And the LHC experiments are looking for those preferences, those subtle biases in how hidden photons interact. Every new piece of data, every limit we set, it brings us closer to understanding this intricate dance between the hidden sector and our own.
Okay, this is all blowing my mind a bit. Let's move on to our next suspect. Axion-like particles, or ALPs. These particles have been popping up a lot lately, even in discussions about dark matter. Is there a connection there?
You're right, ALPs are having a moment, and for good reason. They're closely related to a hypothetical particle called the axion, originally proposed to solve a problem in nuclear physics. But over time, physicists, they realized that axions, and by extension ALPs, could also have the right properties to be a major component of dark matter. That invisible stuff that seems to make up the bulk of the universe's mass.
So we're potentially talking about a particle that could solve two major mysteries at once. That's incredible. What can you tell us about how these ALPs might interact with our world?
Well, our paper focuses on ALPs that interact with our world's forces, like, electromagnetism and the strong force, the force that holds atomic nuclei together. And guess what? One of the ways they might do this is through those temporary bridges between dimensions that we were just talking about.
Oh, wow. So those higher dimensional operators, they come into play again. It's all connected.
It really is. The universe loves to find elegant solutions to complex problems, doesn't it? And just like with those hidden photons, these ALP interactions, they leave behind specific traces in the LHC's detectors.
Do tell.
Yeah.
What kind of traces? How do we actually see an ALP?
Okay, so imagine this. An ALP pops into existence for a fleeting moment. It's born from the energy of a proton collision at the LHC. Then, poof, it decays into two photons, particles of light. It's like a ghost appearing and then vanishing, leaving behind only a faint flicker as evidence it was even there at all.
Okay, that is just cool. And the LHC is sensitive enough to pick up on that flicker.
It is. The detectors at the LHC, they're incredibly sophisticated, able to track the paths and energies of particles with astonishing precision. And they've already been hard at work searching for those telltale photon pairs that would signal the presence of ALPs.
So what's the verdict? Have we found any ghostly flickers yet?
We haven't found definitive proof just yet. But just like with those hidden photons, the LHC has allowed scientists to set some incredibly stringent limits on ALP's properties. Figures 4 and 5 in the paper, those are a gold mine for visual learners. They really show how much ground the LHC is covering in the search for these elusive particles.
I'm looking at them now. It's amazing. In some cases, the LHC is setting limits that are even stronger than what we've been able to achieve through astrophysical observations. Looking for ALP signatures in the vastness of space.
It really highlights the power of the LHC as a discovery tool. And it's not just about finding these particles, it's about what their discovery would mean for our understanding of the universe.
Absolutely. Finding ALPs, it wouldn't just be checking a box on our list of hypothetical particles. This could fundamentally change our understanding of dark matter, the evolution of the universe, maybe even the very fabric of reality itself. Okay, I'm officially blown away, ready to tackle our final suspect.
Absolutely. Let's dive into the world of the incredibly small, mini-charged particles.
Mini-charged particles. Is that just a fancy way of saying really, really tiny?
Yeah.
Because I am all for things that defy our normal scales of measurement.
I knew you'd appreciate this one. In essence, yes. Mini-charged particles, that's exactly what they sound like. They are particles that carry an electric charge, just like electrons or protons. But,
Yeah.
and here's the thing, their charges are tiny, potentially far smaller than even the smallest charge we thought was even possible, which is the charge of an electron.
Okay, now we're talking truly mind-boggling scales. Zooming in past atoms, past protons and neutrons into the realm of the truly tiny. But if these particles are so incredibly small, how can we even hope to detect them?
You'd be surprised. It turns out that even though their charges are minuscule, they would still interact with the electromagnetic force, just with a much weaker grip than regular charged particles. And where do we find the strongest, most powerful particle accelerator that excels at probing the electromagnetic force?
The LHC, of course.
Exactly.
So even these whispers of charge are enough to leave a trace on the LHC's radar. I love how we keep coming back to this idea of the LHC as this incredibly versatile detective, able to pick up on these subtle clues that would have been completely invisible to us just a few decades ago.
It speaks to the ingenuity of the physicists who designed and built the LHC, and to the, tireless efforts of the thousands of scientists to analyze the mountains of data it produces. And in the case of these mini-charged particles, that data is already paying off. Figure 9 in the paper, it shows how the LHC is setting world-leading limits on the existence of these particles, probing regions of parameter space, basically the possible combinations of charge and mass that were completely inaccessible to previous experiments.
So we're filling in those gaps in our knowledge, pushing the boundaries of what we thought was possible. But I had to ask, of all the theories and possibilities we've discussed today, what's the one that really gets you excited? What's the big what if that keeps you up at night?
It's the interconnectedness that really gets me. We started with this idea of a hidden sector, right? A world tucked away from our own. But the more we explore, the more it seems like these two worlds, they might be deeply intertwined.
It's like we've been looking at one side of a tapestry, totally missing the intricate patterns connecting us to something much bigger.
Exactly. And the LHC, it's giving us the tools to start tracing those threads, to see how the existence of hidden photons, ALPs, even those mini-charged particles, could totally change how we see the universe. Imagine if we found evidence that dark matter, something we can barely detect, is actually communicating with our world through these hidden channels.
That's what blows my mind about this kind of science. It's not just about adding new facts to the textbook, it's about challenging the whole framework of our understanding. Embracing the possibility that the universe is far stranger and more wondrous than we ever imagined.
Couldn't have said it better myself. And the best part is, we're just getting started. This paper focused on the LHC, but who knows what other ingenious experiments, what new technologies are on the horizon.
It's like we're explorers setting sail with this compass that keeps hinting at new continents, hidden archipelagos just waiting to be discovered.
And that sense of exploration, that drive to uncover the universe's deepest secrets, it's what makes this field so captivating. Every new piece of data, every limit we push, every theory we propose, it brings us one step closer to understanding the universe's grand design.
It's been quite a journey, diving deep into this world of hidden sector physics with you today. Ghostly particles, extra dimensions, the mind-boggling precision of the LHC. But maybe the biggest takeaway is this. The universe is full of surprises. And the more we learn, the more we realize just how much more there is to uncover.
Absolutely, and that's a truly exhilarating thought.
It certainly is. So until next time, keep asking those big questions, stay curious, and remember, the most exciting discoveries are often the ones we least expect.